All right, so in this lesson, we're going to implement a really cool algorithm, binary search. A binary search allows us to quickly search an array. In this case, we're going to search an array of integers for a certain target or value. The thing that makes this work is the array has to be already sorted. Assuming the array is already sorted, we can go and we can look for a number, and then we can split the array in half, depending on whether or not the number in question is above or below the index of the array. This is super powerful because it basically allows us to completely eliminate half the array right off the bat when we're searching. So as you can imagine, this it gives a pretty good performance boost when we're looking at large data sets. Now, given the fact that this has a restriction on the array already being sorted, you can imagine that we're going to pay that penalty for finding something one way or the other. However, as you'll learn that in future classes, there are data structures that can keep your data sorted as you insert and remove. So a binary search is a great opportunity for taking advantages of those more advanced data structures. So let's dive into the code and see what we got. Okay, so lesson 22, binary search. We're going to leverage recursion because binary search is a perfect example of a recursive problem. Recursion is, if you remember, recursion is where a method calls itself. And in this case, we're basically going to be calling ourself, which is with progressively smaller and smaller parts of the array. So it is a absolutely outstanding thing to recursion is a perfect fit. As always, one thing we need to worry about with recursion is if we are searching massive data sets, we do got to be aware of Stack Overflow. However, most of the time, you're going to be okay because it'd be difficult to get a data structure big enough in conventional memory. I mean, you'd have to have just an insane amount of RAM to cause a Stack Overflow in modern machines. Not to say it won't happen, but it is difficult. So let's go over what we're doing. We have our source and we have our test. In our test, we have a my binary search test, which we'll go over as always. In the main code, we have app.java, which we have to implement. And then we have the binary search interface. So the binary search interface determines what we need to do on this project. So here's the main search method. So we pass in a list of numbers. We pass in the target that we're looking for. So, this would be 1, 2, 3, whatever. This is the target, not the index, right? This is an actual number that we're looking for. And then lower and upper are indexes. So lower is the starting index and upper is the ending index. Now, another two things we have is getNum recursions, getNum comparisons. This is just some data that we're going to collect as we're writing this. This is not, these two functions aren't part of a standard binary search interface. It's just kind of for our own fun, so we can kind of see how many times we recurse, how many times we compare. And it also helps us to know that we have our algorithm correct. So my binary search is where we implement that interface, and as always, I'm not gonna show you that because that is the solution. But let's jump down here to the test. First, let's jump back over to the README. So task 1, complete the binary search class. So that's my binary search that's where that's implemented in. And I give you the algorithm here, right? So this is the algorithm that you need to implement. After you implement the algorithm, then you need to add some stats. And honestly, you can add the stats as you're implementing it. It's not, you don't have to do one after the other, but I typically like to go and, get the algorithm complete first. Then it's just a matter of putting in some calls to increment some counters, right? So we want to count the number of recursive calls and count the number of times our target is compared, right? Now, here's a key. The first call should not be counted as recursive. We only count recursion when we call ourself. So the first time is not recursion. That is just normal method call. So when we call ourself, that's recursion. So be careful about that, because that if you find yourself getting one-off errors when you're going through this right here, like if my solution says 3 and you're getting 4, it's probably because you're inappropriately counting that first call to the recursion. Okay, write unit test, complete app.java. In this case, we just want to be able to have a program that takes an input of integers and then a target to be located. So here's the example input, and then just outputs where the result. The index is found, number of recursions, and comparisons, and so forth, so that a user can play around with it on the command line. So let's go ahead and look at my binary search test. So let's go pull up. Here's the interface. Okay, so let's just read this. Perform a binary search on the numbers list. The list must be sorted before it's passed. You can absolutely, it is invalid for, it is not a valid test to pass in a non-sorted list. It makes no sense. So you don't have to write a test for that. You never have to worry about that. If somebody passes in a unsorted list, that's their problem. That's not something you have to worry about. Okay, numbers, the list to search, target, the target number to find, right, in the list, then lower and upper. Now, if the target doesn't exist, then you're going to return -1. Otherwise, you're going to turn the index inside this list that it exists in. So let's go ahead and open up the test. All right, so the testing I have here, in fact, let's open up the test bench. So you should have a little beaker icon here, testing. And if you don't, make sure that you have your, if this doesn't show up, then you might want to restart your Java, run clean Java language server workspace. So if you clean that usually resolves any problems with that testing icon not being there. So if we click on our testing icon with the test opened, we can see all the different tests I have. And nice cool thing about this is, we can run it, right? So we can we can just run a single test, and we can see run passes, failures. So that's good. Here's another cool thing is I can actually go and debug this test by putting a breakpoint here and then clicking the little debug button. And you should be able to see a breakpoint, which we can now go through and we can see our locals. We can watch, we can see the call stack, some really cool stuff. Okay, so I'm not going to jump into that because I don't want to dive into the solution, but that's some cool stuff right there. So go back to testing. So if I run all the tests, you can see that they all pass. So let's just walk through these. So first I do is I test search lower. Okay, so I use the arrays as list method in the Java SDK, in the Java standard library, to quickly create a list, to convert an array into a list. This is really handy because I can just now hard code a whole bunch of numbers, say arrays as list, and I get a list of integers, and all of the complexity of getting everything correct is handled for me, which is super nice because at this point I'm mainly concerned about testing my algorithm right here, not writing a bunch of array conversion code. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's my sorted array. I declare a new binary search. And you notice here I have the binary search as the interface. I assign my concrete class to that interface. And then I call search.search. And this calls the search method. Now, if we look at let's actually do this, and we'll close that. And we'll close that. So if you see here, what I'm passing is nums, so that's numbers. 2 is my target. Okay, and then I'm passing 0, my lower, which is index 0, and then upper, which is 8. Another thing I could do is I could have done, I could have done nums dot size minus 1, right? That might be even better, because then I don't have to, I'm always going to start index 0, so that can hard code, and then this will will automatically get me my correct index. In fact, now that we made a change, let's go ahead and just run that test search lower, and we will go ahead and run that, make sure everything's still passing, and it looks like it did. So let's go ahead and let's make a test. Let's just. I always like to make the test fail, just because I'm just super paranoid about false positives, right? And that's good, right? Expected 2 but found 1, so that's good. I always have a fear that what I'm doing is passing, but it's silently failing in the background. So that makes me feel better. All right, so let's go ahead and, whoops, that was the wrong button. Okay, so I search for 2, and then here, one thing I do is I have 1 through 9, and then I do 1 through 10. Now, the reason I do this is because I don't want some really weird bug where it works on even arrays and not on odd arrays, right? So here I have I have 1 through 9, and here I have 1 through 10, right? So that allows me to ensure that I'm getting, I don't have any weird errors, right? And so let's go ahead and you can see already, let's take a look. So is this even right? So 2, 0, I don't even think this is, let's do this. So let's do nums dot size minus 1, right? Because size is how many, and we want the index, we want the index. So we go over here, let's do nums dot size minus 1. And we're actually searching for the same number. So we're searching for 2, we're searching for 2. The difference is this array has 1 through 9, and this one has 1 through 10. So that's the only difference, right? So we have an odd array and an even array. So let's go ahead and go with the test bench and just run this test again. Okay, thankfully it still runs, even though I did have a slight error right there, and it all looks good. So let's go ahead and look at the other one. So I have test search lower, which I'm searching for this one. Then I have test search first, right? Now we want to definitely test our corner cases in this particular instance, right? So my first, I want to search for 1, and again I do it with 9 and then 10. So let's actually go ahead and update this code. So from 0 to the end of the array. So it's starting index 0, ending index. Okay. And I'm looking for the number 1, which should be index 0, right? And I'm looking for index 0 right there, index 0. So let's go ahead and run this, test first, search first. Looks like it runs, that's good. And then I do the exact same thing with test search last, right? Test search last, let's go ahead and update this. Starting index is 0, starting index is, and then ending index is the end. And then here, I actually need to update this. I'm not looking for 9 anymore. I'm looking for 10, right? So, and then equals the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm actually looking for index 9, okay? So let's go ahead and say test search last, and let's go ahead and run that. Okay, we're looking good. So I got my first, I got my last, and then I go right in the middle, right? So I'm looking for 5. And this, at this point, I stopped duplicating the odd and even, because I think at this point I feel pretty good about how things are working. So I'm just going to go test right in the middle. So you can see that I'm just looking for 5, and that should be index 4. So 0, 1, 2, 3, 4. So that's correct. Then I test my other corner cases, which is test 0 length, right? What happens if I pass in nothing? I should get a negative 1, right? Because nothing exists. Test 1, right? That's another corner case. If I have just an array of size 1 and I look for it, should be index 0. Another cool test is I could actually do test 1 not found. That'd be another interesting test. Then I have test missing, right? So I add some arrays, so 10, 15, 20, 25, 30, 35, 40, 45, and then I search for 99, which doesn't exist. And let's just keep on updating this, right? And I should get a -1. Test dupes. Now here's another thing is, right, and if you read the specification, duplicates are allowed, right? So now in this case, the way my algorithm runs is I find 1, right? But it's perfectly valid. Another valid answer would be index 0. So as far as duplicates are concerned, you stop as soon as you find any matches. And that's why I stop at index 1, because that's my first match I found. Even though there's a secondary match on 1. So generally speaking, if your algorithm is implemented correctly, you should generally find the first one of the first instance of a duplicate. Okay, then we have test multiple, where I just added in a whole bunch of other, just random stuff that to test for the comparisons and recursions. So hopefully that gives you enough to get started, and I look forward to seeing your solutions. Happy hacking.